our system background. Our lab simulates a spray booth that is located in Dunlap, Tennessee, pressurized by blowers. Both ran by a variable speed motor and ran with the dampers closed. This is our block diagram. Shows our input going into the system as a percentage and our output coming out as centimeters of water. This diagram shows our system. We have 3 booths, all with their own filter, a pressure transmitter, a pressure recording controller, a pressure controlling element, 2 remotely actuated control valves, and the drive motor with both the dampers closed. This is our SSOC with our slope showing our acceptable operating range. Our range that we went from was from 40 until 80, splitting it up in increments of 10, showing the slope between 40 and 50 at 5 centimeters of water over percent, between 50 and 60 at 0.6, 60 to 70, 0.7, and at 70 to 80 at 0.8. Our FOPDT modeling, this is a block diagram showing where our input goes in and coming out, and water is a centimeter as our output. Our pressure step function, this is being shown. The sample is from 75 to 80, showing where our M is our input in percentage, and our change in C is our output in centimeters of water. Step response, here's our gain, which slightly increases as the input range goes up. Our tau between our systems, 40 to 50, 50 to 60, 60 to 70, and 70 to 80, remain somewhat the same. Which tau being our time constant. For our modeling, our FOPT model, our equation for CT, and then our parameters of the time it takes for the jump to occur being 5 seconds, the jump being 5%, our gain being at 0.9 centimeters of water over percentage, our dead time of 0.01 seconds, our tau of 0.1, and that on our system that's an input of 75% and our output is 31 centimeters of water. Here's a sample of our FOPDT plot from 75 to 80. The yellow line is our model input, the blue line is our model output, where the pink line, or purple, is our experimental output. For our gain, it somewhat remained the same underneath 1, except it did once it got to 60, it did rise. Our time constant stayed the same throughout our test region. And our dead time, which remained somewhat the same, 60 to 70, our dead time I think shows because of poor data. Then our sign experiments, we had the input being shown in blue, our output being shown in red, and our change in M was our input, which was 10%, and the change of C is our output. Which was 10. That was for 0.05 hertz, between 60 and 70. At 1 hertz, between 60 and 70, again, our output's in red and our input's in blue, and we kept the change in M, or our input, as 10%, and the change in output dropped down to 7 centimeters of water. And at 2 hertz, we kept the change of M at 10%, and our change of C dropped down to 7. Our sign experiments on our Bode plot, we got an amplitude ratio and a phase angle versus frequency. For our amplitude ratio versus frequency at 60 to 70, we had an order of 2. Our phase angle plot from 40 to 50. Our phase angle plot from 50 to 60. Our phase angle plot from 60 to 70. And from 70 to 80. Here's a model of our amplitude ratio versus our frequency from 60 to 70, where K equals 0.7 centimeters of water over percent, and our 1 over KCU is 0.48 centimeters of water percent, where our FU came out to 2.2 hertz. Phase angle versus frequency from 40 to 50, our purple line is modeling, and our blue dots are where our experiments came out, where our FU came out to 1 hertz. Our FU at 1 hertz. Here's the same thing from 50 to 60 at 2.5. And 60 to 70, 2.2 hertz. Here's comparing our gains for our step response, our SSOC, our FOPD modeling results, and our sign response. Our tau comparisons, which other than 40 to 50, all seem to be pretty much the same. Our step response dead time was pretty much unmeasurable for our comparisons, but as far as our sign function and our FOPD models, and then the averages of our sign, our gain was 0.1, our time constant at 0.12, our dead time at 0.18 seconds, FU of 1.9 hertz, and a KCU of 2.2% centimeters of water. The theory of our root locus show where R, where zeta is our dampening ratio, and our equation for decay ratio. When zeta is less or equal to 1, we're overdamped, monotonic, and stable. When zeta is between 0 and 1, we're underdamped, oscillatory, and stable. When zeta equals 0, we're undamped, with sustained oscillation. Between -1 and 0, unstable, growing oscillation, and less than or equal to -1, we'll have runaway, monotonic and unstable. Our KCD, highest value of our KC that provides monotonic and stable output, which are critical dampening. Our KQD, value of KC that produces 1/4 oscillating decay, and our KCU, highest value of KC that causes oscillating and stable output. Here's the parameters of our root locus from 60 to 70, where our KC is 15%. And KQD is 2.4, and KCU is 3.7. Here we have the ultimate showing our KCU at 3.7, our quarter decay, which is our KC, where KC is 2.4, critical dampening of KC at 0.15, underdamped KC falls between 0.1 and 3.7, and overdamped between 0 and 0.15, and all these are in percentage over centimeters of water. And so for our conclusion, our KC needed, KC will need for overdamped, need to be between 0 and 0.15. Critical, it needs to equal 0.15. Underdamped, KC between 0.1 and 3.7. And quarter decay, KC equals 2.46. Thank you.